Hi guys, so we're back. Should be video number 4, where we're going to start applying our rules to solve some more difficult problems do some more difficult proofs in TFL. I'm going to assume some familiarity in this video with how proof by contradiction works, how conditional proofs work, and how our basic rules besides that work. If you feel a little bit unclear on those, you're gonna want to go watch videos 1 through 3, especially the last one where we cover proof by contradiction, because we're gonna start using it in a lot of ways in these ones. Okay, so the first one we're gonna try is this guy. We're gonna try to prove this biconditional right here. And again, this is from no premises, right? So we're proving this as a theorem. It's a proof from no premises. Now, if you're a student not from UIC and you're trying to look at these videos and practice your proofs, then you might recognize this as one of DeMorgan's laws, right? One of DeMorgan's theorems, that there's an equivalence between these two sentences. And we looked at a case in the last video where we basically understood this negated or statement, right, as showing that both of its individual sentences must be false. And if you have some fluency with the symbols now and things like that, you can see that this sentence is basically equivalent to that. Both of these are pretty much saying neither P nor Q. Both P and Q are false. This one's saying it's not the case that either P or Q is true. And this one is saying both of them must be false. And this is really easy to show with a truth table. That's part of why I like using these proofs as exercises, is because they should be relatively easy to understand if you're familiar with constructing truth tables. And the way to show that these are equivalent with a truth table is relatively straightforward. But in the particular system that we have, proving this equivalence is a little bit of a challenge. So we're going to do that as a way to practice all the rules that we've learned. So first off, this is a biconditional statement, right? It connects two sentences to each other, this guy right here and this guy right here. And so the first thing we're going to be thinking is, okay, we're going to run a standard biconditional proof on this guy. And like I said, we covered that in the second video. So if you're wondering, oh, how do I do that again? Go watch that second video. Refresh yourself on how to do a biconditional proof. Okay, so go ahead and give this a shot. Now's your chance to pause the video, start running a biconditional proof on this guy, and see where you can get with it. Okay, so first thing I'm going to do is I'm going to assume what's on the left, try to show that what's on the right follows from that. So I'm going to assume this guy, negation P or Q. I have to be careful here not to mix up my ands and ors. And then over here, I'm going to put want not P and not Q. So I want to show that the sentence not P and not Q follows on assumption of this guy. Now, in the last video, or I can't remember if it was the second video or the third one, but I basically looked at proving an and statement as proving both of these sentences separately. Anytime you're trying to prove an and statement, you should be able to do that, as I should be able to go prove not P, and I should be able to go prove not Q. And then once I get both of them separately, I can slap them together using and introduction and get my result, right? So how about we do that same thing here? How about we prove not P first? Now to prove not P, maybe, like I said, if you have DeMorgan's laws on hand, that ends up being a one-step proof, right? As you can use DeMorgan's rule and write this down, but we don't have this rule, right? So what we can do is say, hey, what if P is actually true? So here I'm starting another assumption. What if P is actually true? And then I'm going to start fishing to see if it contradicts sentence 1 here. And all you have to do to show that it does is use a quick or introduction on line 2. Right? If the sentence P is true, then the sentence P or Q must be true. And of course, this contradicts line 1, right? Because line 1 says that the sentence P or Q is false. So here I have a sentence and its negation. So this is a contradiction. And this is just restating line 1. So I say, hey, what if P is true? Well, that leads to P or Q by simple or introduction. And this sentence is not allowed, right? It's not allowed by line 1. So I can conclude that this assumption right here, must have been bogus. So I can negate it. I can conclude, all right, P must be false by negation introduction of 2 through 4. So again, I argue here that it's impossible for P to be true because that would lead to P or Q, but that's, P or Q is already assumed false right here. So P is not allowed to be true. Great, that proves not P, right? Now that's one of these done, right? We got not P done. Let's see if you can do not Q. So you can do not Q in a very similar way. So go ahead and try that real quick. If you had a little trouble setting this up, try to see if you can do the same thing to prove not Q. All right, so here's what we're gonna do. We're gonna start another assumption with Q for reductio. And then Q, of course, leads to P or Q by or introduction on line 6, which is not allowed. Line 1 tells me that, right? So I'm going to repeat line 1, and there's my contradiction right there. Right? P or Q as a sentence can't be both true and false, right? And this is telling me that it is. So now you know that this assumption must have been bad, right? Q is not allowed to be true because it leads to this contradiction right here, right? Which is essentially a proof that of not Q, that Q must be false. Negation introduction 6 through 8. Okay, well now that we got both of those, we can just put them together with a and symbol because I proved both of them separately there, right? So this is just and introduction 5 and 9, right? And that's it. I've done this guy and I've proven this whole sentence right here. Great. So this shows me that when you assume negation P or Q, not P and not Q has to follow, right? I argued in lines 2 to 4 that it's impossible for P to be true, therefore not P. And I argued in lines 6 through 8 that it's impossible for Q to be true, right? Because here's this contradiction, therefore not Q. Slap those two together, you get your result right there. Okay, but now we got to go the other way, right? Because if we remember what we're doing here, sometimes it's easy to get kind of lost in all this, but we're proving a biconditional, right? So this whole thing is a proof that negation P or Q implies not P and not Q. But we got to go the other way now, right? We have to show that this thing also implies this thing, right? That's a standard thing you do in a biconditional proof. Again, if you're a little uncomfortable with this, I covered this in the second video, so you can go back and kind of look at that, and there's more examples of proof by contradiction in the third video. So now I'm going to have to do that, is I'm going to have to start, and this is a new subproof right here. This assumption right here is finished. No more, the job is done in line 1 through 10, right? So I'm starting fresh now. I'm going to assume not P and not Q. And I'm going to try to show that negation P or Q has to follow from that. All right, well, yeah, go ahead and see if you can use this. Try to find how you might make this sentence follow from this assumption right here. See if you can get creative and try to do that. Okay. Well, I like and statements, right? Because you can use simple and elimination on them. And this tells me for a fact not P is true, right? So it says not P and not Q. So I can conclude, yeah, okay, not P by and elimination. And for the same reason, I can conclude not Q by and elimination. This is just saying, yeah, okay, both are true. I might as well write that down. Okay. Now, how am I going to get this guy written down in the proof? Well, maybe you've tried a couple things. If you're watching this video working along with this, maybe you've tried some stuff and maybe it didn't work out. So what I can do is prove not P or Q by arguing that it's impossible for P or Q to be true. So here I'm going to start a new assumption for reductio, where I say, hey, what if P or Q is true? If I can show that there's a big problem with this, like a contradiction with this, then I can conclude that P or Q is false, right? So I'm going to try to do that here. And this is really useful, this simple P or Q sentence, because look at lines 12 and 13. This has or elimination written all over it, right? If you assume this sentence P or Q, well, hit it with line 12 and you get yourself Q by or elimination 12 and 14, right? This says one of them is true. And so I can pick this one and say, all right, well, I know already that it's not P, that's true. So I guess that means Q must be true since 14 says one of them is, right? And then you can see maybe right away that that's not allowed, right? Because not Q is already, we're already working with that assumption, not Q. So I restate that here. And this is a contradiction right here, right? Q cannot be both true and false. So that tells me that this assumption was bad, right? So the sentence P or Q in this context is not allowed to be true because it leads to this contradiction. So for that reason, I can conclude not P or Q. I can throw a negation on this sentence right here because it led me into this big problem right here. Okay, so that's negation introduction, 14 through 16. Yeah, and that's all we needed to do there, right? Is we assume this guy on 11, try to show that not P or Q follows. And we did that by pretty much arguing that it's impossible for P or Q to be true under these circumstances, right? It's not possible for P or Q to be true, so that means not P or Q. So what did I do here in 11 through 17? I did the other end of the biconditional proof, right? So I showed that not P and not Q implies negation P or Q. So look, this implication runs both ways now, right? This sentence implies this one, and this one also implies this one. So now I can use biconditional introduction and write my result. Biconditional introduction, and remember we got to cite both subproofs, right? So this is 1 through 10, that's the first subproof, 1 through 10, and the second subproof was 11 through 17. Great. Again, if you're a student and you're not at UIC and you've been given DeMorgan's laws, you can do this thing in like 4 lines, but if you don't have DeMorgan's laws on hand, this is I guess a good way to practice proof by contradiction. And again, I want to reiterate, because I mentioned this last video, I want to reiterate that proof by contradiction is pretty great. We used it all over the place here, right? There's like 3 separate proofs by contradiction. And that arguing that things are impossible lets you churn out results like pretty easily, right? We wanted to prove not P here, so we basically said P is not allowed to be true. That gave us not P. We did the same thing for Q. Q is not allowed to be true because it leads to this contradiction. And then in here, we assume this, and we argued that P or Q is not allowed to be true because it makes some big problems with these sentences right here, right? That let us conclude this, not P or Q. So again, proof by contradiction is your friend. You can use it all the time to prove all sorts of things, okay? Let's do another one. So this is another one of DeMorgan's laws. We're going to prove, going to kind of switch things around now. Oh, well, let me try that again. We're going to do negation P and Q. So this is an and now instead of an or, right? We're going to do negation P and Q, biconditional negation P or negation Q. All right, so this is the exact same flavor as the last one. You know what you got to do. You know you got to run a biconditional proof on this thing. So go ahead and try it out. And maybe now you know what to expect. If you're following along, there's going to be some proofs by contradiction in there. Go ahead and try this thing out. See how far you can get. Okay, so first thing I'm going to do, I'm going to recognize that this is a biconditional statement and start throwing a biconditional proof at it. So I'm going to assume not P and Q, and then I'm going to want not P or not Q. All right. So I want this sentence, not P or not Q, to appear down here in my subproof so that I can close off this end of the conditional proof, right? All right, how do I do that? Well, in the last problem, right, this was an and symbol, everything switched around now. So we can't use the same strategy of proving not P and not Q separately, right? Because this is just saying, hey, at least one of not P or not Q has to be true. That doesn't mean it's not P specifically that's true. So things change a little bit now because we're dealing with an or statement rather than an and statement. So what do we do? Well, what we're going to have to do is show that it's impossible now for this sentence not to be true. So we're going to start a new subproof and negate that guy, not P or not Q, for reductio. And then if we can show that it's impossible for this guy to be false, meaning that this leads to a contradiction, we can go ahead and conclude our result right here. That's what we want, right? And now, this is a negated or statement, right? So last video, I kind of went through an example like this where you can recognize a negated or statement as telling you that neither X nor Y can be true, right? If you have negation X or Y, that means that both must be false. Okay, so if we look at the sentence, not P or not Q, you can recognize that this means that not P must be false and that not Q must be false. And then we also saw a case where these double negations end up meaning that P is true and Q is true. So that's what we're going to do is we're going to look at this sentence and we're going to say, hey, this thing is telling us that P is true and that Q is true. If this is confusing, make a truth table for this guy. And then you can kind of see what I mean. This says neither not P nor not Q, which means that both P and Q should be true. So now we're going to have to use that. Okay, so this is where things can get a little bit weird, but we know that P is true, or that it must be under this assumption, right? So let's prove that P is true by showing that it's impossible now for P to be false. So let's assume not P for reductio. And then, so we're three subproofs deep now. This leads to not P or not Q by simple or introduction on line 3. And that contradicts line 2 up here, right? Line 2 says that the sentence not P or not Q is false. Reiteration 2. Okay, so here I have this sentence, and here I have the negation of that sentence. So this is a contradiction. From that, I can conclude that this assumption must have been bad. P is not allowed, not P is not allowed. That lets me conclude P. All right, so what is that? Negation, elimination, 3 through 5. And I realize the same thing must be true for Q. So let's do the exact same thing for Q and see what happens. So go ahead and try that out if you haven't started already. See if you can do the same thing to prove Q. Then I'm going to buzz through these steps here. I'm going to assume not Q for reductio. Okay, well that would lead to not P or not Q by or introduction on line 7. And of course this contradicts, again, line 2. Right? Because we're still under the assumption of line 2, right? This subproof has been running this whole time, so we're still under this assumption. And this is a contradiction, meaning that this assumption must have been bad, right? So I can take the negation off and say Q. So now we've proven P and Q separately, right? Why do we care about this? Well, if P and Q are true separately, that means the sentence P and Q is true by and introduction on 6 and 10, right? P is true, Q is true, so P and Q is true. But our original assumption all the way at the beginning was that P and Q was false. So let me restate that right here. This assumption that P and Q is false has been going like the entire time, right? So I can restate line 1, and then this is a contradiction, right? So because this is a contradiction right here, what I can do is claim that the assumption at the very start of this subproof right here, this guy, must be false, right? Must be a false assumption right there. So that lets me take the negation off this guy, and then I can say not P or not Q. Negation, elimination, 2 through 12. That's that entire middle subproof right there. And now we're back in the first subproof, right? So if you have longer proofs like this, it's kind of like, you wind up back here in the first subproof and you're like, wait, what was I doing again in here? And remember, we were trying to show this conditional statement, right? We were trying to do a conditional proof in our first subproof, and I got my result right here, right? I showed that not P or not Q had to follow from this. And so I've done my job here. I've showed that not P or not Q follows from the assumption on line 1. Okay, so this is one end of the biconditional. This is, I'm going to turn this sideways for a minute. This is a proof that not P and Q implies not P or not Q. I want to make sure I'm not mixing up my ands and ors there. Yeah, so we've done one end of this biconditional now, right? I'm hoping here I'm not going to run out of room because we're going to start another subproof now, right? Because for a biconditional, we got to go both ways. So we're going to do the opposite now. We're going to assume not P or not Q. And then we're going to want to show that negation P and Q follows. Okay. Go ahead and try this. See if you can prove that negation P and Q follows. And maybe, hopefully at this point, you're already thinking in terms of contradictions and stuff. So maybe we're going to use a proof by contradiction to show that this has to follow. So go ahead and try that. See how far you can get. Okay. So what I can do is say, what happens if P and Q is actually true? So this says not P and Q. So I can say, what if P and Q is actually true? There's no parenthesis there. That's for reductio. What if P and Q is true? Okay, well, this is a nice simple and statement, right? And I like those because it just tells me that P is true by and elimination. And it tells me that Q is true by and elimination. All right, great. So again, this subproof up here already ended, right? It did its job. So this from line 14 and after is all we have to work with. Now, if you're paying attention, you might realize that this is kind of like an or elimination case, right? This says that not P or not Q, one of those must be true, right? So either P or Q must be false, right? But then this says that both are true. So that's kind of how the contradiction is going to look. It's like, hey, wait a minute, this says both are true. This says at least one of them is false. All right, that's not going to work. But here's the problem. Our or elimination rule is defined like this, right? You get an or statement, you find out one of them's false, you can conclude that the other one is true. This is backwards, right? Here we have the sentences in the or statement that are false, and then P and Q are not negated. So we can't just straightforwardly use this rule. The idea of or elimination still works here, but to use this rule, we have to get the negation of one of these sentences. So it has to look like this, not P or not Q. And then we would have to get like not P, right? We would find out that this sentence is false by finding out not P. And then we could conclude that the other one was true. Not Q must be true. So this is just almost kind of like annoying housekeeping that we have to do is I have to take one of these sentences and basically turn it into a double negation version so that I can actually apply my rule here. There's nothing deep going on here. It's just kind of what I have to do in order to use this rule as it's defined. So let me run a quick proof of not P. So I'm going to assume negation P. Again, this was done in the last video, something very similar with double negations. So go review that if this is a little too quick. But I can argue that not P is impossible in light of line 16. This is a contradiction right here. So that means this assumption must have been false, right? Allowing me to put another negation on not P. This will be negation introduction 18 through 19. Now that I have this sentence double negation P, that tells me that negation P right here is false, right? That tells me that negation P is false. So I can go conclude negation Q. Now, by or elimination, lines 14 and 20. But then, there it is. We've already proven Q is true in this subproof. And here I got not Q, and that's not going to work, right? Those are, the same sentence can't be true or false. So I just reiterate line 17 there, that Q is true. Recognize this as a contradiction. And that, where are we at now? We're in the second subproof, right? So that lets me conclude that the assumption of the second subproof which is this guy, right, must be false. P and Q is not allowed to be true, right? Therefore, it's false. If it's true, it generates this contradiction, so it must be false. Negation introduction 15 through 22. And look, that's exactly what I wanted over here, right? Was to show that when you assume this, negation P and Q has to follow. So this, I'm going to kind of turn sideways a little bit here again. This is a proof of the opposite implication, right? Not P or not Q implies negation P and Q. And so now, finally, I'm almost out of view of the camera here, but finally, I can write my result here because I've done the full biconditional proof. It took us through several proofs by contradiction along the way. But there it is, biconditional introduction. First subproof is 1 through 13. Second subproof is 14 to 23. And that's it. Like I said, if you're a student and you've been given DeMorgan's laws, this might seem a little bit appalling, but it's great for practicing proof by contradiction if you don't have those rules. Okay, so just to summarize, we showed that this guy implied this guy through this whole subproof right here, right? And then we showed the opposite, that this guy implied this guy through this whole subproof right here. And to do that, we had to make all kinds of arguments by contradiction. And so if you find this confusing or are not sure about some steps, go through it again, rewatch it, try it on your own. Really, a lot of these steps are very repetitive, but it's totally essential to keep track of what's going on all the way through. Otherwise, it can become really difficult to, keep yourself on track and keep track of what's going on. Okay, we're gonna try one more. I got one more for you guys. And it's gonna be this guy. X and not Y is equivalent to the negation of X arrow Y. Again, no premises, right? No premises. This is a theorem. Now, all of our proofs in this video have been biconditional proofs, so if you think you know exactly where to go to start this, you're probably right. So go ahead and pause. See if you get as far as you can on this one. See how far you can get, and then replay the video and take it step by step with me, okay? So first, normal biconditional proof. I'm going to assume what's on the left, X and not Y. Want negation X arrow Y. Okay. Might as well separate X and not Y using and elimination from line 1. Okay. Now we're trying to prove this, right? We're trying to prove that it's not the case that X implies Y. So I am going to, as always, throw a proof by contradiction to get this result. So I'm going to say, what if it's actually true that X implies Y? So here's another assumption I'm starting, right? What if the thing that I'm trying to prove right now, this guy, is actually true instead of false? Well, okay, if X implies Y, then I get Y off the bat, right? Because I have X up here. X implies Y. And so this leads to Y by arrow elimination from lines 2 and 4, right? Okay. But the problem is we already have not Y as an assumption. So that's restating line 3. There's a contradiction. So that means X arrow Y is not allowed to be true. Therefore, this assumption must have been bad, and therefore I can negate it. negation, introduction, 4 through 6. Okay, well, that wasn't too bad, right? We showed that when you assume this, this has to follow. Because if this inner sentence ends up being true, you got a big problem with this guy. It makes a contradiction, so it's not allowed to be true. It's got to be false. So this is the first side of the thing right here, the biconditional. That shows that this implies this. Now I got to go the other way around, and this I think this side is where things are going to get a little interesting. So I'm going to discharge this assumption right here and start a new one. I'm going to say, let's assume not x implies y. That's this, right? I'm going to assume this and try to show this. Want x and not y. All right, so this is an and statement, right? And if I'm trying to prove an and statement, I should be able to prove both of these separately, right? Because this is just telling me, hey, prove that both of these guys are true, right? It's an and statement, so it's like, prove that both of these guys are true. So maybe I can prove not y first. You guys will see, I think, why I might choose that in a second. But let's try to prove not y first. So let's assume that y is true to the contrary, right? So for reductio. Let's assume that y, reductio. Let's assume that y is true. Okay, well, lines 8 and 9 are all we have to work with. So you might be thinking, well, Eric, where does this get us, right? Like, what can we do with this sentence y? Now, in an old video, we showed that if you got some sentence like this, you know, this is like a sentence that's living in your proof somewhere, you can do a quick conditional proof like this. You can assume whatever you want, restate that sentence A, and prove that B implies A, right? So if you're already given a sentence like this, pick anything you want, and you can prove that this thing implies this thing simply by restating this sentence you already had. So maybe you can see where I'm going with this, right? Is if I have y already, I can run a quick conditional proof that x implies y. So I got y, and then I said, hey, look, if you have y, you can prove that x implies y simply by assuming x, want y, you know, then you restate y. That proves that x implies y. And this should make some sense, because if I already know that this statement is true, there's no way that this guy can be false, right? Because this guy being false would require, by the truth table definition, right? It would require that this is true and this is false. But A, I already know is not false, right? So it kind of should make sense that you can prove, you know, once you have A, this sentence has no choice but to be true. So I got x implies y there. Why is that important? Because we've assumed that it's false up here. So we restate negation x implies y, like this, and this is a contradiction. You have a sentence here, and then the negation of that sentence there. So that tells me that this assumption that started the subproof is bad, right? It's wrong. This y is not allowed to be true because it leads to this. So then I can conclude not y by negation introduction, lines 9 through 13, okay? All right. So that's done, right? I got this little guy done. So that's kind of like half the battle, right? Is, you know, I wanted to get x and not y, and I got one of them. So I got not y done, okay. So how am I gonna prove x now? Okay. How am I going to prove x? This is where things are going to get a little bit weird. So this is going to be kind of a challenge. But first thing I'm going to do, because I'm looking at this and I'm not sure where to go, I'm going to start a proof by contradiction for x. So I'm going to say, let's assume not x. So this is going to be for reductio. There I go again, reductio. Okay. Okay. Now where do I go? Right? I've assumed not x. I'm starting to fish for a contradiction. And what could I contradict? Well, I mean, I'm in this subproof starting at line 8. There's always this guy to contradict, right? This could make the contradiction, or not y could make the contradiction. The rest of this subproof was kind of over and done with, right? This was just to prove not y. So I'm going to contradict one of these two. I just haven't figured out how yet. So here's what you can do. We ran into a case like this in another video. Let's say A implies B. This is equivalent to the sentence not B implies not A. These are called contrapositives. These two sentences should be logically equivalent. Yeah, we did some kind of problem where we basically proved this, not exactly, but we used this fact. So I'm going to say contrapositives. So, you might be thinking, well, who cares about that? This is the statement x arrow y, right? But I know that it's equivalent to the sentence not y implies not x, right? Because they're just contrapositives of one another. Again, I encourage you to, I know if you're a student at UIC, maybe you haven't heard this term yet, contrapositives, but I encourage you to make a truth table to show that these two mean the exact same thing. They're logically equivalent. They mean the exact same thing. So look at this now. I can prove that not y implies not x. Let me do that. So I'm going to assume not y again for the purpose of proving this thing. And of course, just like last time, all I have to do is restate not x. Yeah, this is a restatement of 15. And that gives me not y implies not x. 16 to 17, right? Okay, now this is important because this essentially will contradict this, right? Because this statement is equivalent to the statement x implies y, right? And I've already assumed that that's false. X implies y is false. So I'm getting real close. I'm going to have to change now from the contrapositive to the ordinary x implies y. Okay, so now let's try this. Let's try running a proof that x implies y. So let's try assuming x, want y, right? Okay, I'm like 3 subproofs deep now. All right, so I can't pull y from anywhere directly, right? Y appears up here, but this assumption has ended already. So I can't pull it from up there. So what I have to do to show that y follows from x is a proof by contradiction. Surprise, surprise, right? So let's say y is not true for reductio. Well, in that case, not y implies not x, right? So I can use that to get not x by arrow elimination on 18 and 20. But then of course, I've already assumed x to be true right here, right? So I'm gonna restate 19. This is a contradiction. And so what that means is that this assumption must have been bad. So I can take the negation off of it. Sorry, where is it? This guy. I can take the negation off of it and write y, right? It's not possible right now for y to be false. So I can write y by this, 20 through 22. And then what does that do? That proves that x implies y, right? Because that was the whole idea of this third subproof right here, is that I assumed x, I wanted to show y, and I did. So this is arrow introduction from lines 19 to 23. Arrow introduction from lines 19 to 23. And then what's the problem with x implies y? Well, look all the way back up here at line 8, right? I've assumed x implies y to be false. So I'm going to restate that now. Restate line 8 right there. Okay, this is a contradiction. So what was the bad assumption? Let's go all the way back up here to the start of this subproof right here, not x. And this shows me that this assumption must have been bad. So I can take the negation off of it. I'm really running out of space now, so let me do this. I can take the negation off of it. Negation elimination from this whole subproof 15 to 25. What was going on with that? What was the whole idea of this thing? Well, I wanted to prove x, right? All the way up in this thing. That was the whole start of this other end of the conditional subproof, is I wanted to just prove x along with not y, and I did, finally, right? So this gives me this result, right? You can combine x and not y. Not y appears on line 14. X appears on line 26. So I cite 14 and 26. And that gives me this result that I originally wanted up here, right? Okay, and this concludes the other end of the biconditional proof. This is that negation x arrow y implies x and not y. Okay, so you can look at this thing in its full glory here. This is a very long biconditional proof, right? Runs from lines 1 to 7. And then the other end of the biconditional took us about 20 lines. It was from 8 to 27 there. So finally we can write the result. X and not y imply each other by biconditional introduction. And then both subproofs, so 1 through 7, 8 through 27. Now, if you were paying attention in this guy, you might want to stop me and say, well, Eric, wait a minute. This was the assumption of not x right here, right? And then inside that assumption, you assumed x. How are you supposed to be able to do that, right? You're already assuming not x. Why can you assume x? Like, that doesn't make any sense. And if you notice that, then that's great. But you're allowed to assume x because basically you used all the rules correctly, right? All I was trying to do in this little bit right here was go from this to its contrapositive, this guy, right? That's all I was trying to accomplish in this proof right here. And so really it doesn't matter that those two assumptions contradict each other because I did everything correctly, right? I used all the proofs correctly. This was specifically in the context of showing that, x arrow y is really the same as not y arrow not x. So you can do things like this. Occasionally it can be a little bit confusing, but everything was done correctly, right? All the rules were applied correctly. So this is still a totally good way of getting this result. And yeah, that concludes this proof. So I want to finish this guy by saying that if you're a student at UIC and you're watching this, probably you're not going to have to do something this hard, okay? Really, this was so that you can have a little challenge. If you're trying to study, you can get some practice there applying proofs by contradiction, conditional proofs, learning equivalences between things like, contrapositives and things like that. That's all going to be very useful. But if you see this, I hope you don't sweat too much. It was just the purpose. This was made for the purpose of just practicing everything in a really long, tedious problem, just to kind of get yourself used to using things and making assumptions and keeping track of those assumptions. So yeah, I hope these videos were helpful for you guys. Yeah, if you have any questions or anything, you got my email. And yeah, that's about all we're going to do for these proofs. So good luck studying. And yeah.